Now let's look at the third, which also is the last example for charged line. Now the line is folded in a ring shape and the line is uniformly charged. The ring has radius of r. The total charge is q ring. Point P is at the distance x above the center of the ring, and we are going to find the net electric field at point P. Here I have a simple sketch. The ring has radius of r, and from the center of the ring to point P, the distance is x. We can define the angle between the x-axis and the line connecting the point P to the ring as phi, and the distance from the ring to point P as little r. Using Pythagoras theorem, this r equals to square root of x squared plus big R squared, the radius squared. Now let's look at a side view, a face-on view. So now we are facing the ring, and the x-axis is pointing outward. So when I have a dot, it means the arrow or the vector is pointing outward, out of the page. And when I have a cross and circle like this, it means the vector is pointing into the page. So that is just a side note for the notation. So on this sketch, I have the x-axis that is pointing outward. Now I'm going to break the ring into small pieces, and I'm going to choose two elements. Let's take this element and this element. Let's call the charge of the first element dq1 and the charge of the second element dq2. The electric field due to dq1, it will be pointing outward and downward. So I can only draw 2D. You have to use some imagination. The angle is outward and it's pointing downward. This is my DE1. Similarly with my DQ2, the electric field at point P, it will be outward and upward. And let's call this DE2. So now the two vectors are like this, at an angle, and it's outward. Now we can use the symmetry again. The angle here equals to the angle here. So we can consider two small elements on either side of the ring, and when we add up the electric field from these two small elements, the off-axis components cancel. We can pair up all the elements so that the net electric field will only have the x component. So now we only need to focus on the x component, Ex, which equals to integral of dEx. And the integral is over the ring, which equals integral of Coulomb's constant times dq divided by r squared, distance squared. And since we are focusing on the x component, so times cosine phi. Using the triangle we have here, cosine phi equals adjacent over the hypotenuse, which is x over square root of x squared plus r squared, the radius squared. And note that the x and the r, they are both constant. The x is the distance from the center to point P, and r is the radius of the ring. So they are constant in this integral. So we can put them outside the integral. Then this equals Coulomb constant divided by r squared, and r squared is x squared plus r squared, the radius squared, times cosine phi, which is x divided by square root of x squared plus radius squared. Then integral of dq. And the integral is over ring. So a quick note. This x squared plus radius squared is the distance squared. And this whole thing is the cosine phi. So now the integral left is only dq, integral of dq, which means we only need to add up the charge over the ring. And it was given that the ring has a total charge of q ring. So this equals Coulomb's constant times x divided by x squared plus radius squared to the power of 3 over 2, then times Q ring. And that is the net electric field since it only has the X component. And finally, that was the last example for charged line. In the next lecture, we are going to look at charged area.